I guess we start with announcements. We have an assignment due on Wednesday. And that's about it. Other than that, we're in the middle of our between exams crunch of information. So last time we were getting some extra examples of the context-free pumping lemma. The one we were on was showing that the language WW, where we have the first half of the string and the second half of the string as identical subcomponents, is not context-free. We looked at a good string to pick. And since the subset of people who are here right now is, I guess, intersect the subset of people who were here yesterday is the empty set, I can ask, what is a good string to pick for this? What should we choose as W, such that WW becomes easy to show that it is not context-free? What the? Ooh. I got an EWU alert, system-wide test. So it shows up like this. Interesting. Good to know. Any thoughts? Good string to pick? I don't know. So the one that was suggested yesterday, which was a good idea, but turned out not to work, was AB to the M, AB to the M, with parentheses around AB. So M repetitions of AB followed by M repetitions of AB. And we struggled with that because there were cases where you could have a certain number of ABs to be VXY, and it meant that you would always keep something in the language as you did this. So we found a better string was A to the M, B to the M, A to the M, B to the M. The reason this works out so well is we can break this down into 3 cases. We know that the length of VXY has to be less than or equal to M. So that means that we only have 3 cases. VXY is all A's, all B's, or some A's followed by B's, or some B's followed by A's. So really 4 cases, but 2 of them are going to turn out to be very similar. So we need to find some number of pumps of the recursion of a non-terminal to a non-terminal, such that when we do that, we lead to a string not in the language. And we need to do that for all 4 of these cases. So I equals 0 will work for each case. I equals 2 will work for each case. Literally any value of I that is not 1 will work for any of these. But we're going to move forward looking at I equals 0. So if VXY is all A's, then we take out some number of A's. Since the length of VY has to be at least 1, we're taking out at least 1 A, either from the first group of A's or the second group of A's. If we do this, then we have an unequal number of A's between the first and second groupings of A's. So we can't have A to the M, B to the M, A to the M, B to the M. We end up with something not in the language. So mapping between this first and second for all A's makes a ton of sense. Exactly the same logic works for B's. If we take out at least 1 B from the first set of B's or the second set of B's, then we end up with an unequal number of B's between those 2 sets. So we can easily see the resulting string is not in the language. Now it's worth thinking, all right, we take out a chunk of A's and B's. So VXY is either comes from the overlap of these A's and B's, these B's and A's, or these A's and B's. So if you do that, a chunk of A's and B's from either the first half or the second half means we don't have an equal number of A's between the first and third segments, or an unequal number of B's between the second and fourth segments. whichever, you just show that whichever one you go through. So if the overlap is here, then we compare these A's to these A's. If the overlap is here, we compare these A's to these A's, or these B's to these B's. If the overlap is here, we compare these A's to these A's. So we know it contains at least one A and at least one B. So wherever that overlap is, there's another part of the string that we can refer to as not being the same. Questions on that? Does that make sense? And this is just talking about the middle section of B's and A's. So regardless, in all four of these cases, we end up with some easy way to show that the resulting language, when you don't go through that recursion, cannot produce a string in the language, which means that such a grammar with such a recursive set of productions, I guess is what I want to call it, recursive set of productions, can't exist. And since this string is longer than M, which stands for the number of productions in the grammar, then that shows us that such a grammar can't exist, because we picked a string that is longer than those number of productions. If those productions are in G and F, then they can only produce one terminal each. So there has to be recursion somewhere in there to be able to produce a string that is that long. Since there was no such recursion, since we proved that no such recursion can exist by breaking it down into the recursion has to happen somewhere in one of these places, we showed that none of them can be the case. That tells us that such a grammar cannot exist. Show of thumbs, how intuitive is this? Does it make sense as to what we've done and how and why? This just tells me how much more detail to go into.
I mean, like, I see the connections from the past and I see how it works now that you showed it, but like, I don't think I could have done that without being told.
Sure. The hard part is picking the string. I feel like that is the really intuitive step. But do you feel like the rest of this flows from that pick? I think getting an intuition of what to pick is just practice. There's not really an easy way to see that or visualize it. The intuition that you want to use is that if you're passing a window of size M over this, then you want the string to be such that any possible window of that, there's an easy way via some value of I to show that by taking out Vy of them or increasing by some multiple of Vy, that leads you to having some way of showing that the resulting string doesn't adhere to this form. And that's really tough to do, to pick a string that's going to be able to show that from the beginning. But how do we feel about the rest of this? If you were given the string, does the rest of this come into place? Either of you look like, yeah. Both of you look like, I want to be asleep. So I want to give you a little bit of a visual for it as well. So here's the visual. We have MAs followed by MBs, followed by MAs, followed by MBs. We know that VXY, this section, has to be at most M characters. It can show up anywhere in the string now, not just at the beginning. So we have to say anywhere that it could show up at any size between Vy being one character and VXY being M characters. So Vy could be M characters if X is empty. Then we show that no such recursion can exist. Ready for an example? Ready for another example? All right, a to the n factorial. How could we possibly show that this is not context-free? Again, the hard part is, what is the string? What do we think about the string? Anyone have an idea for what we might want to pick for the string here? There's really only one point of attack.
+1.
So it needs to be in the language. How do we know that m+1 a's is some factorial? We need this to be some factorial value, whatever we pick. And it has to contain m somewhere because it has to vary based on when your opponent in the game says a grammar with this many productions exists. You need some way of generating the string that becomes the counterproof to their idea of how many productions are in the grammar.
So n needs to be a function of n.
Yes. Really intense shades.
Yeah.
What do we think? Function of m. We're going to want to run with is a to the m factorial. That really is the only point of attack. We can't construct a factorial that isn't based on m. And regardless of what you pick here, a to the m-1 factorial, a to the m+1 factorial, they're all going to work. It's just a matter of, it's ever so slightly harder to make it work. So I think a to the m factorial is a good choice, but here's how you pick the string. We need something that has an m in it. It needs to be in the language. We only know that something with m is going to be in the language if we take the factorial of m. It's the only way we can know for sure that the string we pick is in the language. So how could we proceed now that we have a string? We need to break down into cases. What could vxy be? But in this case, there's only one case. Because the string is all a's, vxy can only be all a's. If we're writing the notation for this, we want to break down the number of a's that come from v and the number of a's that come from y. We're going to call them k and l. We could now, if we do this, write an expression for how many a's are outside of this loop. So uxz, the string that isn't produced with that recursion, has to be length m factorial minus k plus l. Does that make sense as to why that is? But this also must be in the language, right? This is saying that we've gone from the start non-terminal to the recursive non-terminal, skipped the recursion and gone directly to the termination of the string. We did not iterate that recursion. So UXZ needs to be a valid string in the language. How many A's are there? It's m factorial minus k plus L. So what we can conclude from this, since we're making the assumption that this language is context-free and it is a proof by contradiction, we can assert that m factorial minus this k plus L is equal to j factorial for some j, because this string needs to be in the language. So if we want to proceed, we need to show that it is impossible for m factorial minus k plus L to be j factorial for some j. We know k plus L has to be less than m because of the constraint of the fact that the length of Vxy has to be less than or equal to m. So k plus L has to be less than m. We can show that m factorial minus k plus L is greater than m minus 1 factorial because of this. Just by using this inequality, we can show that no such j exists for that j factorial. It is not possible. So all we have to do from here is conclude, saying we set up this equation that must be equal to some j factorial. We showed that there is no such j that satisfies this expression, and that means that this string UXZ is not in the language. If that is the case, then no such grammar can exist. This is the same as setting I equal to 0. We just did not iterate the recursive non-terminal. How are we doing on this example? Does this make sense? Show of thumbs, maybe? Mostly makes sense. It is okay if it does not. I just need to know how much more detail to go into, or to cycle back on something and explain it, or ask questions. Any questions or concerns on the example before we move on to the last example? Any clarifications? All right, last example. A to the n, b to the j, such that n is equal to j squared. So we'll start in the same place. We need to find a good choice for the string that we are going to pick. Once again, there aren't a ton of points of attack here. So what is a valid string that we could pick?
The m squared and bpm.
That is an excellent idea. Let's run with that. So now I'm going to give you a few minutes. And in fact, you could all work together on this, and that might be useful rather than working individually. But go ahead and put your brains together and see if we can come up with the logic that is going to show that no grammar can exist, no context-free grammar can exist for this language. How many cases do we have for Vxy? Three cases. I agree with that. Could either be all A's, some A's and some B's, or all B's. We just need to be able to show that regardless of what we pick, given some value of I, it is impossible that string is in the language. for each of those three cases. And you can pick a different I for each of them. The all A's case and all B's case is pretty trivial. M minus at least 1 squared cannot be equal to M squared. M squared cannot be equal to M squared minus at least 1. But what if we have the some A's and some B's case? Is it possible to pick an exact overlap of A's and B's such that when you take it out, you still have exactly some new value squared A's and some new value B's? It's actually a really good question, isn't it? Is that mathematically possible?
At least not nearly.
So we need some way of taking out some number of A's and some number of B's such that we end up with, is it possible to end up with M minus 1 squared A's and M minus 1 B's with a particular overlap? What is the minimum size? What is the difference between M minus 1 squared and M squared? Is there some formula that we could use to figure that out? Basically, the question is M minus 1 squared, sorry, the difference between M squared and M minus 1 squared. So M squared minus M minus 1 squared plus 1. Can that be less than M? Setting it as a value to give you an idea of what this is. So if M is 10, we would have 100 A's, 10 squared A's, followed by 10 B's. The overlap needed to get this to M minus 1 would be 9 squared A's, followed by 9 B's. That is a difference of 20. M was 10. So we cannot take out 20 things. We cannot take out 20 characters. We can take out at most 10 characters. So that, in that one example, wasn't possible. Generalizing that to any value, is there ever going to be a difference between M squared and M minus 1 squared, plus the 1 that we need to remove from the B that's going to be less than or equal to M characters? All right, 3 choices for VXY, all A's, some A's and some B's, all B's. Arguments for all A's and all B's are trivial. We've seen this before, but the argument for some A's and some B's is significantly more difficult. And the reason is when V is made up of all A's and Y is made up of all B's, If the length of v is 0, use I equals 0. This reduces down into the all b's case. If the length of y is 0, use I equals 0. That reduces down into the all a's case. Otherwise, neither length of v or the length of y is 0. So you have to go down into showing that m minus the length of y squared is less than or equal to m minus 1 squared. Exactly this concept that we were trying to say. So we can expand this, give them all on the same side of the radical, and say that this is m squared minus 2m plus 1, which is less than m squared minus the length of v. Because we showed that the length of v here is somewhere between 1 and m. So we can show that because of this, the result cannot be an L, solely because we can't subtract v from the m squared of y and get something that gets to m minus 1 squared. Ugh. And now we have shown every possible case. How are we doing on this example? Does this make sense? Does this need more explanation or iteration? How are we doing on this one? There are other ways to show this. This is just one such way to actually break this down mathematically or logically to show it. But I felt like it was probably going to be one of the easier ways to see it and visualize it. So this is much more of a challenge problem. This is something that is probably harder than I would throw on homeworks or on exams, just because it requires a bit of mathematical manipulation. And I would rather focus on, do you understand the process than do you have the background to be able to put all of this together? But where this is actually used, you will find examples like this where you actually need to use and manipulate math in order to come to that conclusion. We are dead today. Very quiet. Any questions before we move on?
I think I got it intuitively enough, but didn't know how to.
Yeah, yeah. All right, the last thing we want to talk about with regards to context-free pumping lemmas is for linear languages. So we saw this distinction between linear and nonlinear context-free grammars, but we can also make the distinction just straight up with the languages themselves. So we'll call a language linear if there exists a context-free grammar, a linear context-free grammar for it. So this is a subset of context-free languages. Every linear language is context-free, but not every context-free language is linear. So context-free language is a bigger circle. I guess I can show the big circle of context-free languages. The subset of linear languages is smaller than it. And inside of it. Do note that kind of like with a DFA and NFA, or I guess a DPDA and an NPDA, if you derive a nonlinear grammar for a language, doesn't necessarily imply that it's not linear. A linear grammar may still exist for it. So if we wanted to prove that a language is not linear, we need to prove that no linear grammar can exist for it. So this requires yet another pumping lemma, but this is not a pumping lemma we're going to go into detail about. I just wanted to let you know that it exists. One very important difference in what this pumping lemma looks like compared to the context-free pumping lemma, and that is we could say something like, here's the exact pumping lemma for linear languages. Let L be an infinite linear language. There exists a positive integer m such that any string w in that language with the length of that string greater than or equal to m can be decomposed again into uvxyz with the following constraints. Here's the difference. UVYZ now can no longer be greater than m. That has to be less than or equal to m. So the entirety of getting from the start non-terminal to the recursion and iterating the recursion once cannot be longer than the number of productions in the grammar. That is true for all linear languages. Just as before, length of Vy has to be greater than or equal to 1. That's the length of the recursion. Now we can see, again, that uv to the I x, y to the I z must be an L for all possible I. What's the difference? What does it imply? I just talked about it. Pumped substrings have to be within m characters in the left and right ends of the string. Now, middle string x, whatever is the route from the final recursion to terminating the grammar, that can be of arbitrary length. And the logic for this is very similar to the logic for the context-free pumping lemma. You would use the same sets of skills for solving those problems to solve the pumping lemma for linear languages. So again, no homework or exam questions on this topic, but presented for context of whatever the class of language is, there exists a pumping lemma to show that a particular language is not in that class of languages. And this is the last we will ever talk about pumping lemmas in this class. Thankfully. I don't think it's anyone's favorite topic, but it's a very important topic for the theoretical results that we will come and use these results. So it's useful to at least see how it is done. All right, very short slide deck here we can get through in next to no time. We're basically done with context-free languages. We've seen now everything that we need to see about them. Just a couple last fun facts and fun ideas surrounding context-free languages before we move on to an even larger class of languages. So the questions that I might have are, we have some context-free languages. What could we do with them? And how can we use set operations on them to help us better understand them? So can we union context-free languages? Can we intersect context-free languages? Can we find the difference between context-free languages? What are the guaranteed results of the associated language? What do we think about this? Would the union of two context-free languages result in a language that is context-free, guaranteed to be context-free? I have. That actually is true, yeah.
I want to say, yeah.
It is, because you can add a single rule to the grammar that says basically S arrow S sub 1 or S sub 2, where S sub 1 is the grammar for the first half of the union, and S sub 2 is the start of the grammar for the right side of the union. And since that is a legal extra rule you can make, the result must be context-free. What about the intersection? It's interesting to think about. Let's actually talk about it in general. So context-free languages are closed under, and what we mean by closed is if you have, so for a union, we have a context-free language, union, a context-free language. If the result of that is a context-free language, then context-free languages are closed under union. That is what that means. They are closed under concatenation. You concatenate a context-free language with another context-free language. The result is a context-free language. They're closed under star closure. You take a context-free language and want to repeat it an arbitrary number of times. Any string that is viable in that language, followed by concatenated with another string, concatenated with another string, concatenated with another string. That is all context-free. Context-free languages are not closed under, we're right, intersection, complementation. So the intersection is certainly an interesting thing worthy of more discussion, but I will show one last interesting result first here. So the intersection of a context-free language and a regular language is guaranteed to be context-free. We know this, but no such result exists for context-free language intersects context-free language, which is interesting because you know that that intersection is just a subset of that language. But there's no guarantee that you can define that subset with that same set of rules. Thankfully, this rule of the intersection of a context-free language and a regular language actually becomes useful in strange side cases like this. Show that the language L is, I need to superscript these, A to the N, B to the N is greater than or equal to 0, n is not equal to 100. Is that context-free? That would be a pain to show otherwise. But we could rewrite this as an intersection between a context-free language and a regular language. Right? A to the N, B to the N is context-free. A to the N, B to the N is equal to 100 is a regular language. We're just looking for 100 A's followed by 100 B's. You could write a DFA for that. It would just be a really big DFA. Long sequence of A's, transition, long sequence of B's, back to a final state. There's exactly 100 of them. You could show that it's the case. And we know regular languages are closed under complementation. So the reverse of that so what would the grammar for this look like? It's kind of gross, isn't it? You have to be able to say no at exactly n equals 100. What would the NPDA look like? Disgusting. But we can instead use the intersection of a context-free and regular language if we can refer back to this rule that that intersection is guaranteed to be context-free. Makes the proof way easier rather than writing out a 100+ production grammar. So you can use this intersection rule to prove that a language is not context-free by contradiction at times. And this is a way to shortcut the pumping lemma. Some of these rules exist because we know how painful the pumping lemma actually can be. Whenever there is an opportunity to bypass the pumping lemma, it's worth recognizing that that exists. So here is an example. Show that the language W such that the number of A's is equal to the number of B's is equal to the number of C's is not context-free. Do note, we could use the pumping lemma for this. Take a second and think about what would that look like? How could we use the pumping lemma for this? We have an annoying number of cases. All A's, all B's, all C's, some A's and B's, some B's and C's. But that's it. We can't have A's and C's. We can't have A's, B's, and C's, because if we're using the string A to the M, B to the M, C to the M to do it, then that's a lot easier. But we could first assume L is context-free. If it is, we can take the intersection of it and the language A star, B star, C star, which is regular, and end up with a context-free language. If we take the intersection of the number of A's, number of B's, and number of C's, and A star, B star, C star, that says all the A's have to come before all the B's, which have to come before all the C's, we end up with A to the N, B to the N, C to the N, which in example 1, the last set of slides, we proved was not context-free. So we reduced this problem into that problem by making use of that rule. So the contradiction was found. Basically, if this language were context-free, then this language would be context-free. Since we know that that language in 3 is not context-free, then the example language is not context-free. There are certainly some limitations to this that are a little bit frustrating. So the first one is that no algorithm exists for determining whether 2 context-free grammars generate the same language. Think about that for a second. That's kind of a simple question to ask. Did these 2 grammars produce the same language? You can imagine writing an algorithm for this. What would that algorithm look like? Right.
That's just defining.
You'd actually have to generate every string in the language and see, can that string be generated by this grammar? Can that string be generated by this grammar? As soon as you find a counter example where this grammar can generate it and this grammar can't, you're done. They don't produce the same grammar. They don't generate the same language. However, what if they do? Is this algorithm ever going to terminate for an infinite language? There are always more strings. You haven't found the counter example yet. When do you terminate and say, yes, they generate the same language? You can't. You just don't know if you found the string that is not true yet. You have to use some other method of doing this. And it's straight up, you can't. Which is interesting. That was literally it to this, this very end slide deck. Was just some interesting things about context-free languages. And this leads us a bit more into our discussion about the theory of computer science that we will have over the next couple of weeks. I forgot to download the next one. All right, the class of languages we're going to look at next is the languages that are accepted by Turing machines, because Turing machines are the foundation of theoretical computer science. So we've seen 2 major classes of languages. We've seen regular and context-free. We also saw that there was a class of deterministic context-free inside of context-free and linear that is also inside of context-free. But these are the 2 major classes of languages we've talked about so far. The only difference between the state machines that represent these languages is that in an NPDA, we carried a stack along with it, and we made operations to the stack as we moved across those states. That was the only change between how we referred to a DFA or NFA and an NPDA. Other than that, it was basically the same idea. However, the question that we might pose is, are there more powerful language classes that could be represented if we were to allow some different kinds of storage devices in our automata? For instance, what if instead of taking along one stack, we took along two stacks? What if instead of taking along two stacks, we took along three stacks? What if we took along a queue? What if we took along an infinitely sized binary search tree? Any data structure that you can think of, we could attach to some kind of automata and allow for anything that we could do to that structure to be done as part of a transition between states. You could bring along a hash map. Why not? So how far could we push this? What is the most powerful possible state machine? The answer to this is the Turing machine. It is the most powerful possible state machine. If something can be calculated, a Turing machine can calculate it. If we can write a program, that program can be simulated on a Turing machine. This is the basis for how computer science came to be. The model of a digital computer is based off of this idea. And it's amazing that we can actually simplify it as much as we can. The most powerful possible state machine can be shown relatively simply as a storage device, kind of like a DFA or an NPDA. However, it's going to look very different from either of those. So storage is now on an infinite one-dimensional array in both directions. Instead of starting at index 0, we're going to start somewhere, and there's infinite tape to both directions. Each cell on this tape, think of it as an array index, is going to hold a single symbol. This tape stores some initial information. So the tape is going to have some information on it when the program starts. We can read from and write to this tape, but we have full freedom to do so. So we're going to be looking for certain symbols to be present. We're going to be writing symbols to the tape as well. This means that we have no restrictions on moving left to right. In our other classes of languages, we had to read a string from left to right. We're going to be relaxing that constraint with a Turing machine. We have no input file or output storage other than the tape. So if we need to produce any kind of output, it has to go on the tape. The input to the program will exist on the tape prior to beginning the instructions, and all output will be on the tape by the time the machine halts and finishes. So the way to visualize it is something like this. We have the control unit that's going to keep track of where it is in an internal state representation. So what we've thought of as the DFA or the NPDA is all going to exist within that control unit. As it finds itself in certain states, reading certain things on the tape, it's going to make some decisions about what state to transition to and what to write on the tape. We will come back to this tomorrow, getting the formal definition and start seeing how we can produce some Turing machine programs. I have office hours starting now if you have any questions on the homework that is due tomorrow.